Yeah, my biggest accomplishment of today, database performance, the only one. Why? I think if you are not working on databases every day, but every now and then, you have these moments maybe you're developed something and it was nice, you deployed it to live, you start working on something else, and then you're just nicely working on it. Speaking of mic, I'm not used to hand-hold mics, right? Do I really need mics for the recording, or can I just speak up and it'll be fine? I need it, okay, thanks. So you're working on something nice, and then you get a phone call like, hey dude, do you remember this application you developed half a year ago? Yeah, performance is pretty bad at the moment, so I need you to jump in right now. And when I was a developer, I thought these moments were extremely annoying. So now as a DBA, I have some more knowledge about databases. So today was a good moment to share 3 things about how to prevent these things from happening. So hopefully at the end of today, you get less calls about performance issues you have to jump on immediately. So let's see where we get. Right, a little bit. This is me. My name is Derk van Veen. I'm a database specialist within Adyen, so which means I'm basically playing around with databases the entire day. That's what I came for, and that's a lot of fun. And basically, a big part of my job is getting the databases fast. Keep them into the green, keep them into the red if red needs more speed. But we would like our databases to be fast, very fast. And I will just share you a few of the insights. So today, we start by asking the right question. Because if you ask a stupid question to your database, the database will do what you ask. It doesn't do a lot of work, it will not be fast. Then without indexes, it's hard to talk about performance, because if you need any kind of performance, indexes are a need to have. And finally, we have to talk a little bit about SQL. If you are in a foreign country and you're not speaking the language and you get lost, it's really hard when people start to explain where you need to go, but you can't hear them. So if you're in the country of databases and you're not speaking SQL, it's hard to get around. So you have to talk a little bit about it. So asking the right questions. And these days, the first question is really easy. It's always this one. Can't we just have more hardware? Especially with the cloud vendors these days, adding hardware is easy. And a lot of the times, do I need, or can I add more hardware? Maybe the answer is you need to add more hardware. I've been creating databases as a cloud vendor, and you get 3 IOPS per gigabyte. So if you need a little bit of IO performance, you need more gigabytes, or you need to pay for more gigabytes. So I was creating 10, 20 gigabyte databases, but we were paying for 250 gigabytes. So at least we get enough items. So yeah, sometimes hardware is necessary, but at the end of the day, more hardware can't make up for poor design. And I like this one. The fastest way to do it is just skip it. And maybe it doesn't count for single queries, but I've been analyzing processes like we do this every day, and then there comes a moment in time where the process takes 25 hours to process 24 hours of data or work, and then it becomes annoying. And at one of my jobs, I was analyzing this entire chain of things which were happening, and I found this part of 6 hours of work. I was like, what is happening here? Asking the person next to me, like, what is this job doing? Yeah, we used to have this report, but I'm not sure whether we are still using it, so, right, what if we skip this part and see if anyone starts complaining tomorrow and next month? So, yeah, that was an easy way to win 6 hours out of the 25. One of the things you can skip is very important. It saves time for free. And this is one of my favorites. And it's the Brontosaurus pattern for those who are into databases, dinosaurs. I'm into databases. And usually this pattern applies to screens. Let's say you're a customer and you are doing financial transactions. You give us a call, we open this page with a shows you as a customer and it shows your last 10 financial transactions you did. Maybe if you don't spend a lot of money, we can cover 2 days. But then we open the same screen for an account like Uber. So the customer is Uber, but Uber has a lot of sub-accounts. Like they have taxi drivers, and they are all over the world. They are with tens of thousands, hundreds of thousands, millions. And all these taxi drivers make a lot of payments. So you start with one account, then you have all the sub-accounts, the drivers, then you have all the financial transactions they did ever over the years. Then we sort all these financial transactions in time, and then the screen shows the top 10. And then my colleague complains to me, like, this screen is so slow. And I replied, like, don't you think it's amazing that the database can order this billions of financial transactions in just 5 seconds? I think it's amazing. Yeah, but the screen is slow. Now maybe you should ask a different question. If you want to show 10 random financial transactions for an account like Uber, because if you reload the screen, you get 10 completely different transactions, so it doesn't matter anyway what you load. So don't collect them all, order them in time, and then show a random sample. For me, that's asking the wrong question to your database. And then there are 2 types of queries which can kill performance on your database. And this one is the easy one. It runs at the end of the month. It's the method. Everybody knows what time it starts, what it is doing, when it's coming. Actually, if you listen carefully, you can hear it the day before. It will be there, right? But there's a second type of query which can also kill your database performance. And these are mosquitoes. If you camp in Scotland with your tent close to a lake, it's this beautiful evening, there's no wind. You have the midges. Midges are very, very tiny mosquitoes, but they are with tens of thousands, and they attack you with all of them together. And then you're just will be miserable. It's the same with databases. So I've been working for an insurance company as well. Actually, we were making software for insurance companies, so we were hosting databases for basically all the insurance companies in the Netherlands. Do you know the mosquito of our database? The most executed query, the most expensive one, is getting the language. Do you know how often an insurance company changes language? I can tell you it's less than 10 million times a day. You can do this once, and then you can skip all the 10 million times minus 1 times executing this query. So don't do it, right? Maybe you can check this once a day, if you want to be sure they didn't change language. But I've been working there for 8 years. They haven't changed language. And then this one. Keep it stupid, simple. We have this extremely high available application. Multiple entry points directing you to 2 different application servers, having 2 different load balancers, having 2 different databases, having 2 different storage layers, and everywhere where these process. And I thought, like, this is slow. Well, I thought, like, you have a lot of components. Do you need to make all these processes everywhere? Well, they explained that is to make it fast. No, to make it high available. And I thought, like, but if we straighten out all these lines, would the entire configuration not be much easier? And they said, yeah, it looks easier, but why would it be faster? I would say easier is faster, so let's try it out. So that's what we did. We put in 1 day of work, and it was 8, 9 times faster, I think, just by making the entire configuration easier. So if you have 2 solutions, and you have to pick from them, and you don't know which one to pick the easier one. If you can explain it in 2 sentences, it's probably a good idea. And then this one. Process your data close to the source. And that does not mean everybody needs to have fat databases or fat database clients. But I've been working with a developer, and he had this very fast caching algorithm. And he thought, like, I can beat the database. So he did a performance test on his laptop, and indeed his caching algorithm was faster than one in the database. Then the application went live, and the application server went immediately out of memory. Because on his laptop he had a few records in table A, a few records in table B. Then he was joining them and that was fine. Then the application went live, he was loading 10 gigabytes from application A, 30 gigabytes from table B, and for some reason that was not enough to fit into the memory of the application server. So there is a balance. Don't join on the application, but join on the database. If you can do smart things on the database, do them over there. Find the balance. And then I always get questions about this one. I have this screen and people can search, but they can search on name, dates, whatever fields, and they always pick a weird combination, and then it's really hard to get good performance. How do we do this? How do we fix this? And I always tell them, like, don't allow your customers to search on everything, because if there's one combination which has poor performance, a customer on a day will be able to find it. So try to guide them. Don't give them all the options, if not all the options is what you need. So this is the first part of things you need for good performance. And I know this is a challenge because you will be here and you don't know each other. But if you discuss this with your neighbor right now, then you will be sure you will remember it. So just take a minute, talk to the scary person next to you about a case where this applies to you. And I will give you 2 very uncomfortable 2 minutes. All right, this is already 2 minutes. It's pretty great to see that most of you got that really scary first. All right, let's talk about indexes. And to explain how indexes work, you need a little bit of history. There once was a time where not every person had a mobile phone. So if you wanted to call that person, you needed to call their house and really hope they were available and picking up the phone. And these phones had a very tiny memory, like one record. You could read out the number and that was it. So if you want to call somebody, and you don't know the number, there was a very smart solution, and it was a very thick book. This book was delivered at your house, if you had a phone, every few years. And this book was ordered. First it was ordered by city, and then by last name. So if you wanted to call my house, you went to Delft, then search my last name, so you find a list of people named Van Veen, like me, and then if you know my first letter, where you can call me. That was the way to get a phone number. And that's how indexes work as well. First they are ordered on city, then on last name, and then you can quickly find the records you're looking for. But it doesn't work the other way around. If I give you a phone number and a phone book, the only way to find the single number in the phone book is to go from page to page and check all the numbers. So that's how indexes work. They work in one way, they are very efficient. The other way around doesn't work at all. So when do we need an index in a database? I would say that's really easy. Every time you create a query, or someone creates a query, if there's a where clause, you put the column in the where clause. No, you put the column in your index. It's already in the where clause. So you put them in your index. If you have two columns in your where clause, you have to put two columns in the index. Which one do you put first? Well, you put in the most restrictive one first, because you want the database to do little work. So if you can find a single record or maybe 10 records on one column, but you would get thousands on the second column, that's not too that's efficient. But if you get already 1,000 rows from the first column, you have to do work for 1,000 columns, which is just more work. So always put the most restricted one first. And now I know most technical people are a bit lazy. So they think like, if I have a where clause and I have a column in it, I need an index on it. So can I don't just create an index on every column? Oh, you can, but they come with a price tag, because an index is an additional data structure. It's like you have the phone, but also the phone book. And the phone book also takes a bit of space. You need to refresh it every now and then. You need to get a new one, so you have to do maintenance for it. So I would say don't add indexes in all columns, because you won't need it. The only moments where you need an index in your on your column is if you have a where. You have to put them on the joined columns, and you have to put them on all the columns for the foreign keys, and that's it. Having more doesn't give you any benefit, but every insert and update has also be processed into the index, and that's just work, and it takes time, so just don't do it. Don't do the work you don't need to do. Then if you want to know whether your query is efficient, you can use explain plans. An explain plan is named slightly different over the multiple database flavors, but every database flavor offers you this. Basically, it tells you, like, dear database, tell me what you're about to do. So I downloaded a DVD database from the internet. It's a free database, it just gives you some data and you can play around with it. And here I say, dear database, show me how you collect all the columns and records from the table film. And then you get a row like this saying, I will read all the data, I will return 1,000 rows, and the cost is 64. And 64 is just a number. It tells you a little bit, but definitely not everything. But on the same server, if this number goes down, you're making your query faster. If this number goes up, your query will be slower. And this one is important. What is the cost for this particular query? So in this case, I am collecting 1,000 rows, and the cost is 64. Now we do something fun. I can read a single row from this table. But the funny thing is, it's more expensive. So now I have only one row, costing me 66, and reading everything is 64. That doesn't make any sense, right? Why is this? Well, the where clause is telling I need a specific row, but I still have to read them all, but on top of it, I have to do some calculation. Is this the one I need? So that's what's making this query more expensive. But I already teach you the trick. If you have a where clause, you need an index on the column in the where clause. So let's create an index, leave in the query, and now the cost is 8. So it's already 8 times faster with an index. This is a very tiny table, but the performance difference with and without index is already a factor of 8. So this is why hardware can't make up for poor design. Of course, this is a very easy example, but let's make it a little bit more complicated just to practice a little bit. So I add a single join to this query, and I want to know what's happening. There are two ways of reading this plan. You can read it top-down or inside-out. I always start with inside-out because the database starts working with the most indented line. So the database will start here. Why does it start there? Well, the result set is only one. Result set of one is always little work, so let's get started there. So we have one row, we hash it, and then using this hash, we join the column, and then finally we have to return the results to the user. And this is what I always start with, but I do it very quickly. And then, when I know more or less what's going on, I start reading top-down, because the top row is telling me the total cost for this query. And then it's like follow the money, but then follow the cost. But follow the money is much more fun. So the total cost is 91. So the cost is not here. The cost here is 28, so that's quick. This one is also hashing. It's just a few CPU cycles, cost is almost nothing. Then this one is expensive. Out of the cost of 90, 70 is coming from here. What's going on here? Well, I'm reading all the data from the table. Reading all the data is expensive, so we need to fix this. How do we fix it? It's a join column, we need to add an index, so let's create the index, rerun the plan, and now everything is much faster. So this is how you analyze queries. I know it's a very quick once, and it's a very easy query, but this is a process to analyze what's going on within your database. And this is how you decide, is this query fast or not? All right. There's one more trick to this. Sometimes you're looking at the plan and you think like, hey, the plan is good, but the query is slow. Sometimes there's just a mismatch between what the plan is telling you and the reality. How does this work? Well, the database is using statistics to determine what a fast plan is. But if your statistics are bad, like your statistics are telling, yeah, this table contains 5 rows, so you will get a maximum of 5. In reality, there are thousands of rows or 10,000s of rows. So the database will make a very poor estimate. So if you have a big difference between explained plan and reality, you need to update your statistics. And then, with good statistics in place, there's no garbage in, there's no garbage out. So hopefully, this is enough to get you fast performing queries. Right, SQL. But before SQL, talk to your neighbor. Tell a good example where the lack of an index really caused you issues. Or how did you fix this problem from 16 hours to 2 minutes? How did it give you a minute and a half? Because it's not true. Right. How's it like when you're having a conversation with your neighbor?
Yes.
All right, talking a little bit about SQL. I already mentioned it. Thank you, very comprehensive. I was just being more patient. I have to admit your method is more effective. Talking a little bit about SQL, I'm wondering, like, how many people are working with databases like daily? Any developers? Oh, also like half, 50-50. Right, so just for the developers, maybe I'm preaching in the wrong church here, but I would say knowing the SQL is important when you're talking to databases. And I've been talking a lot with developers lately. I even meet developers who say, like, yeah, I don't actually know what kind of database is behind my application. To me, that's really scary and weird, but then I try to explain them, if you don't know the flavor of your database, and you execute the same query to one flavor or the other, the result set can be different. And they're like, yeah. Works for me. So I usually say that I usually get something like this. I don't need SQL. I have ORM. It's doing all the work for me. And I have to admit, ORMs are doing a good job at generating queries. And if they don't, they give me this answer. And I have to admit, a ORM in combination with AI, I think even Aiven has an AI tool to optimize queries, but I'm not sure. Our colleague tried to convince me in December last year. But yeah, they go a long way, and they can do a lot of tricks. But the problem is, if they generate a single poor performing query, what are you going to do? Because one poor performing query can blow up the screen, the application server. And if you don't know the language, who do you need to talk to? Well, you can talk to me and colleagues of mine, and they charge you a lot of money, and they're happy. But I would say, if you're working with databases, any time at all, just spend a little bit of time on learning the language, because SQL really is a very powerful language. So don't start here, because if your application is doing this all the time, you get all the columns from this table. But you can't skip columns or rename columns. So if this is what your application is doing all the time, and you're calling me for help and you're having a performance problem, well, you're not tying my hands to my back, but at least in my front. Because I can't do any modifications to your data model or pretend the column has been dropped or delay something. Because you're always getting all the columns back. And if there's someone needs a column and your data model doesn't know how to handle it, you get an exception. And that's where the story ends. So just spend a little bit of time, just specify the columns you need. It makes life much faster, especially when you really need it. And it's not that much work. I think you can convince your ORM to generate a list of columns for you. I'm pretty sure. And then, if you're learning the language and you're learning indexes, we can have some fun. I have a number of sets of queries which are given exactly the same result set. But one of them is much faster than the other one. So here I have an example where I can have two columns in the variables, or I can have a single function, but then I need to check only a single value in the variables. So we all have two arms, so you can put one arm, put your arm up matching the side on the screen, which is faster. Everybody has two arms. Just guess. No, one. Just one. Right. The first one is faster. You have two variables to check, but they are directly in the index. So you can basically start reading from the index until you have the correct date. Then you keep on reading until you're at the end date, and then you stop reading only for the index. Well, on the other one, you are using a function to retrieve the year from the date. But there's no function, there's no index on the result of the function. So the only thing to do this, for most database flavors, is read all the data, get the year. So it's much slower.
Couldn't verify because of type.
Sorry, I missed the questions.
Extract here with return list and then schema. The type is different, right?
Yeah, the type is different, and you are using a function to extract the year from the date.
So that will be int.
That's it.
That's int, right? That will be int.
That is an int.
And
Yes.
I have one chart. I couldn't have.
No, it would not fail. But all the queries are correct and doing it. I picked the DVD rental database, so you can do actually all of the work at home as well. So you can install Postgres, get the DVD rental database out, and then run all the queries, and then you will see everything. Right, another one. I am reading from the table customer, and I want to have only the active customers. And active is a boolean, and yes, both ways are valid ways of referencing a boolean. But one of them is 4 times faster than the other one. You can pick one, left or right. Everybody agrees on the same one. And it's the correct one. Second one also works, but you have to do cost. You have to cast from this var to a small int, and casting takes a little bit of time. This one is my favorite, because AI is not able to do this. One query is way more complicated than the other. You have the additional where clause. And yes, there is an index on return date. Left or right?
How many records match last update counts?
How many?
So for that particular date, will I get a lot of records?
Yeah, I think it's a lot of records. It's all the records after 2006. So basically that's half of the database.
Do we have compound index?
It depends, really. It depends on the index that exists.
There's no index on last update and there is an index on return date.
Sorry.
There is an index on return date, but there is no index on last update.
Can I get the other microphone?
But it depends.
Otherwise, this is not.
It's only if the right one has less than 20% of the queries.
Thank you. So index in Postgres works only if it's less than 10% of the data set, then it uses it, and then if it's less by statistics, then it will use index, and therefore that will filter by return date. Otherwise, if that's more, then it's xcan, and that really depends on the CPU cost.
I would say it's more depending on the I/O cost, but yeah. In the example on the right, yeah, left, right, and right. Here you have to rate everything because there's no index on last update, so there's no way to rate all of the data. On the second hand, you're adding a column which has an index, and you know you can do this because you know the application. A AI tool will never suggest this solution to you because it doesn't know it can actually cheat using a column with an index. So this is a good pattern to know, and you can only do it as a human understanding the design and the application. But it can really make a big impact on the performance. All right, and yes, this is also a valid. You're not holding up your hand because you know which one is faster. You have a question.
I had a question on the last one, sorry. Can I go back? So in this case, the order of the indexes matter, right? So the first one is not part of the index.
Yes.
Correct. So will the second column still be indexed on, and that would make the query faster? Because in the first case, then if both end up scanning everything, then there's more operation to be done on the right one, so that one should be faster, right?
Yeah, I tried to make a point, a little bit of cheating with this database, but yes, of course, there are a lot of circumstances making one or the other faster. But it's about the end. Right. Again, it is valid syntax, tested it. It's in the SQL, what do you call this, the string with the SQL document. Which one is faster, the union or the or clause in the where? Left or right hand?
It depends on the database, to be honest.
You know, it depends.
Come on, everybody has 2 hands. Pick one. Pretty much split. And indeed, it depends on your database, but definitely one is much easier for the optimizer to handle. And that's the one with the union. Because for both parts of the union, you can use a single index, and the database will immediately know what index to use for it. For the second one, if you are using Postgres, it's doing the same decomposition of your query, ending up with the same time and the same cost. So in Postgres, it's equally fast, but there are many databases where when queries become more complicated, then it's better to use this one because it's much easier to handle for your database. And then it's not really part of knowing your language, but
Can you go back to the previous one? Because they might actually give a different answer. The left and the right query. Because if they match both predicates, they show up twice in your union.
no, if you do a union, all they show both up, but if you do a union, the duplicates are fine.
But you counting them.
Yes, I was equally suspicious as you are about the syntax, and I checked it out.
I think you're double counting, but we can take it offline.
We can take it. We can take it offline. I can handle that. If I'm wrong, I would like to know why, because I was having the same thoughts, like this can't work out with the duplicates. My research said I'm fine, but I would like to have another look and prove myself wrong. That's always fun. All right. If you are working with your database, please use transactions. You know, auto commit can be easy, but building transactions is a good habit. It's outside of scope of this talk, but it's close to my heart, so I want to tell you anyway. I think it's important. So, yeah, if you have more questions, this is a very good moment to ask them. Floor will be run around with the microphone.
I promise to run around.
All right. Then I have one final note for you why knowing SQL is important. This is a very small piece of code. You start a transaction, you're checking someone's account balance, and if the balance is high enough, you subtract that amount, and then you commit your transaction. And this is why a company got bankrupt. This is not a safe way to get money from an account with the default default transaction setting on your database. You have to do a refer update or increase the serialization level. So with this in mind, if you're a developer and you know nothing about SQL, I hope this one story convinces you to learn a little bit about SQL so you can prevent your company from going bankrupt. Thank you very much.
Write a ledger, don't keep balances.
Sorry?
This is another tip. Yeah. Don't keep balances when you're doing this, but make an actual ledger so you can keep track of transactions.
It's about the problem itself and not.
I know, but this is like all over the internet. No bank does this.
I know.
Because this is like has so many faults. So please don't get this as examples anywhere.
I'm Claude Warren, and for anybody who's heard me talk before, people know that I start by talking about my family, you know, that I'm not the one on Wikipedia. That's my father. Look him up, you'll find my mother, you'll find my brother, and I'm going to talk about my brother. I'll get to that eventually, but I'm not going to do that tonight. So, instead, I'm going to tell you a little bit about my history and how I got here. And,
A little closer.
a little closer? Okay.
A little closer.
Maybe this mouse coming up here, and that's not good at all. This is technology, isn't it wonderful? The can you hear me? You can hear me, right? Okay, I'll speak up. Oh yeah, long ago in a city far, far away, because as you can hear, I am not from around here. Actually, in the 80s, in the city of Denver, Colorado, I happened to live there, and there's a science convention there, and there's a group of crazy people. One of whom is build a well at Martin, Maryland. They made stuff with the space program. Actually worked on the extravehicular device that, you can back around in space. But Bill Llewellyn was far enough up the hierarchy in North Marietta that they would send him to conferences, and low enough that they wouldn't give him business cards. So he printed his own business card, and it said, Bill Llewellyn, mad scientist, North Marietta, Denver, Colorado. And he handed those out at a conference. And he knew he had made it when he got a piece of mail addressed at work, addressed to Bill Llewellyn, mad scientist, North Marietta. And at that point, he realized that he needed to have a mad scientist club. And so he founded one in Denver in the mid-'80s. And I was a founding member of that club, hence all mad scientists have that codes, hence the lab code. Well, in '87, the mad scientist, Bill Llewellyn decided we should have this thing, we all decided we should have this robotics competition. It's called the Critter Crunch. And if you look it up on Wikipedia, you look up Critter Crunch robotics, you'll find an article about it. That was the very first tabletop robot competition, first combat competition with robots. Precedes Robot Wars by about 10 years. And in fact, they cite it as an early reference. It has open source rules and the whole bit. It's a great thing. Okay, so I competed in that, and it's all of the things on the shoulder. And Critter Crafters was the name of our group, and we had a wonderful time building tabletop combat robots. Fast forward a number of years, and I get married and whatnot, and my wife has a disability disease, and so she's losing her mobility over a long period of time. She right now her foot drags, so she has trouble walking from place to place. So we live on one floor. We don't have any carpet. It's great. Okay. So, but she makes her tea in the kitchen, and then she needs to go move to wherever she's sitting to consume her tea. In the process of moving, because of her dragging foot and other issues, she tends to spill. It's a good thing we don't have any carpet. So I thought, why not? And I have this robotics background, it's not really robotics, but why not build an autonomous chair-side table so that they'll follow her into the kitchen, she can make her tea and put it on the table, go back to where she's going, and it'll follow her along and hopefully not spill the tea as much as she does or will. This is the goal. And I started working on it, thinking about working on it about 6 months ago, not quite that long ago. And I thought, okay, I can use a Raspberry Pi to drive this whole thing, and we'll have sensors to do all the sensor stuff. And I made this work. I've done sort of similar stuff, but nothing quite to this level. And I think that I discovered that I overestimated my capability. So I started out and I got this kit. It has all these nifty bits and pieces you put together to make robots, make sensors. So there's an echolocation distance sensor in it. And I thought, okay, I can use that to figure out where the obstacles are. And I did some experiments with it to see how well it worked, what kind of data it gives back. And it's really interesting. It'll tell you there's an object 60 centimeters in front of you. All right. But that's a point. It's a point in space. And so I could say, all right, well, I know there's an obstacle there, but how big is the obstacle, and how am I going to map all of this? So my goal here, if you think about this, is that I want to build a robot that's going to build a map from nothing. We're going to start at zero and know absolutely nothing, and we're going to build a map. And we're going to be able to move around in the environment based upon the map that we build and the fact that we're following somebody else. Okay, so I'm thinking about this, and I thought, okay, I've got all this data that I have to track, and I'm not really sure exactly what I'm going to have, because I may have different sensors later, different types of data. So I think about this a bit, and I come back to my firm belief that all data is a graph. I don't care what you're working on, all data is a graph. And even if you tell me, oh, it's a tree, I will point out that that is just a reduced graph. So it's a graph, don't worry about it. So I decided that I would do what I tend to do is to use RDF, Resource Description Framework, which is this really nice graph. It's an Apache project that has a reference implementation. They will run on the Raspberry Pi, it's written in Java. It's very small memory, we have large memory. It's a nice little project. The advantage is that it only has 3 columns, so I only have to have 3 indexes at most for the whole thing. It's not quite true, I'll flash that for a bit. And it's all done internally anyway, so I don't have to worry about that. But what I can do now is I can then say, okay, this is an object, this is an obstacle. And all I know about the obstacles is at this point. And then I thought about it some more, and I thought, this is a graphing, this is a mapping problem, which is the other kind of graph. And so how can I solve this graphing problem? And so I picked up the geometry library. Use the geometry library, got this nice graph. But now I have this problem of, if I think about it some more, I have a problem of when I find a point that's an obstacle, I have to make sure that it's actually there. Could be a phantom one, which isn't so much of a problem if I'm just planning right now to move. But it also might be that there's a door, and the door can be open or closed. Right? So if it's open, there won't be an obstacle, but later there might be an obstacle. Or maybe there's an obstacle now, but later there won't be an obstacle. So the environment will change. So what I've built is a layered approach. Now I'm used to that. Layered approach. So I have this planning layer, and this is where I put all the data that we get from the sensors. And then down here, this is the ground truth layer. GT, like little fast cars. When I start out, there is nothing in the ground truth layer. And the more I think about it, the more I think there never will be. Because I don't have any way to know what's really there and what isn't. But I can tell, there are things that I will know. For example, I build this up, and we build a graph, and we figure out how to get from point A to point B, and then I have this path that I took, and I can then simplify the path and make it the most efficient path I can, given the graph, the map that I've got. I can put that down here, because that's more truthful than this is, right? So the idea, concept of layers of truth, and I'm not sure how many there are here. But as you move down, these are things that are more true, known to be more true than these things. So, if I think about this for a bit, what I did was I built a simulation. Why not? All right. So my simulation, I built a box, a room, and I put this barricade in the middle of it. And I put that's where we are, and this is where we're going. And I said, basically, find a way there. Now this is, I put this as in the sensor, the fake sensor. And so when the fake, well, I call this the fake sensor would give it some points based upon which way the robot's facing and a number of other things. So when we start off, we get a point that's here, we get a point that's here, we get a point that's here, we get 1 or 2 over here, and I think there's another one over there, something like that. And so now if you think about how you're going to do this mapping, what's the most efficient way to do this map is you would go and you build a map using A star, so you can figure out the fastest route to get there. But to do that, you have to go to all those points. Right? So you have to go over here, and you have to calculate how far everything is, and figure out which of these 2 paths is the most efficient. You don't want to do that with the table. Right? You don't want the table running all over the room to try to figure out how to get there. So instead, I just have to pick a direction and start based upon what it's got. Now, the other problem I have is that when it moves, it takes another sensor reading, we're going to get some more points out here. Eventually going to get lots of little points, but there's no way to tie them all together and say this is a solid object. Except that this thing has a width. Right? There is a physical size to that thing. So I know that whatever this graph, whatever this map is going to do, the resolution has to be at least that big, right? So this space happens to be the width of that, as I've read this a long time. But anyway, what I did here were all these points that we find for obstacles. You should look at this and you say, okay, that's less than the space, the resolution. So we put those two together, and it builds this set of things that are linked together, and it just draws lines between them effectively on the little diagram that I do. And as it runs, it's really great. It runs along, and then it builds this out, and it builds this out. It actually finds this whole wall. And it actually, what it does is it actually steps up here, and then it goes over here a little bit, and it says no, and then it runs back over here, and runs over here, and then it goes. And so this is the course it finds, and in the process of doing that, it actually maps out this much of the space. Actually, puts a little bit over here too. Okay, so at the end of that, simplify this path, and I can put it here. And now later, if I'm standing anywhere near here, instead of just saying, how far are you from the target, we also ask, do we have any paths that are anywhere near the target? And follow the path. Okay? And if at some point we're following that path, and we discover that this is a door, and we close the door, okay, then I'm not sure what we do with this. We can either remove it, or we can refactor it, so we put the door in it. At that point, it's going to decide to go this way. Right? We'll have two paths. Have to make a decision. So this is the goal, and this is the start of the solution that I've got for this. Okay, so I have this part. I have mapping actually worked. I fell out of my chair the night that it worked because I had all kinds of problems using. I was using geospacing, the Sparkle. The query language for RDF graphs is called Sparkle, so it's like a SQL but different. Just it's better. It's all pattern matching. It's wonderful stuff. So I've gotten to the point where I think this thing works, and I started to started to assemble all the bits and pieces, and now I have a Raspberry Pi, and I've got an Arduino, and I've got motors that, when I tried to run them last weekend, they didn't work, so I don't know what's wrong with that. But what I found is that I think it really is true that all data is a graph, because I can do this in a graph. I can come in and I can later annotate any of that data in the RDF graph. So I can add new data to the graph. I can, if at some point, the other goal here was to make this all local first, right? It's all got to run without connecting to the internet. But if I connect it to the internet, I can have it find things that are out there, that's out there. So if I want to run outdoors, I can have it attaching map information that's outdoors and be able to pull that into the graph and query it without a whole lot of effort. So that's basically where I was going with this. So how did I get here? I thought I knew what I was doing, discovered I wasn't, and then figured out that I can do all of this interesting bits and pieces. And hopefully somebody's going to come up to me and say, yeah, you can do this way. It's going to be really easy. Maybe 20 people as an answer. And I thought, and coming up with this idea that we can have ground truth and maybe never get there, but be able to build models in the RDF graph. And the thing about the RDF graph is that you have a data set in the RDF graph where you can have multiple graphs, and you can query all of them at once, or you can query some of them. So like I can just query this one, or I can query the whole stack. I can say where are all the obstacles, and query the whole stack. I can say, what have we found in this path? And I can just query the one I've got here. I can look at, what do we know from the last couple of runs? And just query that far back. And it's a very handy way to reduce your data set by changing just the layers of the graph that you're looking at. How many people here have actually worked with RDF graphs? Anybody? Okay, one. That's about the way it works, isn't it? I have people ask me, why RDF, why not use a property graph? And my answer is that no matter how much you think you know about your data, when you start, or even when you're done with your project, you're wrong. You don't know it, you don't know all of it, you don't know how your customers are going to use the data, you don't know how your customers are going to use your application. Won't be surprised. But if you have a property graph, or I think property graphs suffer from the same problems that XML has, in that in XML you come in, you think you know what you're doing, and you build elements, and you have properties of elements, and you have sub-properties, or sub-elements, child elements. And then you get your project out there, and somebody comes around and says, that property you had, it really needs to be a sub-element, and now nothing's going to work because all of your queries are broken, right? Because now you have to query the child element, not the property. So it becomes a very big problem. In RDF, you don't have properties. Everything's at top level object in the system. So all the queries are the same. You want to add something, add properties to a property, not a problem. You can do that. In RDF is quickly here. It's very simple. It's a subject, predicate, object model. So it's very simple declarative sentence. I can give you a number here. I didn't know name, log. Okay, so now that this ID has a name, Claude. So you got to be me. And then you would have, other things. Anytime you find out something about me, your date of birth, you just add it. You find out that you want to know, what city I'm in, fine. You want to know who lives in the same city, not a problem. This is a very straightforward Sparkle query, and they work really, reasonably fast, fairly fast. And you can do some very interesting research with it. I worked in a project in Ireland a couple of years back doing cancer research. And my job actually was to make a query engine for these cancer researchers. And what they were doing was they would have equipment that ran their experiments, and they would generate data from that. They would convert that data to write it out as RDF. And then they would be able to attach that to the query engine as part of their query. And the query engine would be able to match graphs that were published match it up to graphs that were published on the internet. So we had, there's a model out there of all drug interactions. There's a database of all medical publications and what drugs they dealt with in their articles. There's massive database on molecules, they call it, as opposed to drugs in the model. And so we were able to query all of that data and mix in the researchers' data. So they can do things like, this is my favorite query. One of the researchers found something that killed the cancer, and it also happened to be lethal, so it wasn't going to work for people. But they were able to run a query that said, find me a drug that looks like this and has been published in a journal in the last 5 years. Right? And the system could do that and query across all those databases and come back and give them the answer. So I'm a big proponent of RDF, and I've used it in a number of interesting projects to show that you can do almost anything with it. And I would recommend anybody who hasn't used it to take a look at it. It's a little different. You have to think sideways, I think, to make it work in some cases. And it's a little strange. Anyway, so my goal is to finish this up, actually, finish this all up. I'm hoping that maybe by 2 or 3 months from now, I'll have a table that wanders around the house and follows my wife around and carries the tea for her, and hopefully doesn't spill it very often. So that's how I got here, and that's what I had to talk about. Thank you.
Maybe if you'll entertain us with questions or suggestions, or people that want to put money on this, or words of don't know, in defense of SQL, I don't know. Anything's possible.
I was wondering, how are you tracking your wife?
How am I tracking my wife? Yeah, well, you know, like me, she doesn't like to be tracked, so it's going to be an interesting problem. I think what we'll end up doing is we'll already RFI type tag, something that's near field that she'll be able to go next to it and say, okay, follow me now, and it'll follow her. But I've got all the RFID stuff there. I haven't played with it yet. I got this really cool box, and I bought this box. All the stuff you need to build a robot. And it lies, but it was fun to play with anyway. So.
Does she know about the budget?
Yeah.
Wait,
It's kind of hard to hide it in our apartment because I spend all the time working on it. And she's, yeah.
I have one question. If you look at the information that you're trying to store, then the information is living in the sense that the situation in your room changes. So if you look at those layers that you're talking about, then their truth, their value to your model is dependent on their age, for instance. But you could also infer that if a fact stays the same for a longer amount of time, then it's closer to your ground truth.
True. Absolutely.
Okay. So this is, to me, more akin to a vector problem, in the sense that, like AI, you have certain facts that are more true, that have more weight or value to your model. So I'm wondering why you're not going that way with this, because I like REF as a theory, as a principle. But the problem is that it's to me, as a SQL guy, something that is more a variable way of adding data to points, so like variably adding columns to certain aspects of your data. And in that sense, it's very specific, very specialist, niche. And I think that if you go towards a vector approach, you'll find that more tools are there, and that you will be able to get faster results to where you want to go, even processing work.
Perhaps. Being on a Raspberry Pi and all of that really limits the space that's available in memory for high stacker processing. It's just not that much on it. I should be clear, I'm running a B3A.
Sure.
Right, so it's not the red, not the 4, not their high power, it's small. And
I appreciate that. But in this case, if this is very important to you, throw Raspberry Pi 5 and the problem will be done.
yeah, it's small, but
Was here all the time.
Any more suggestions? What about ASUS?
no.
I like their simulation that you drew, and the nice thing of simulation is that there's very little error rate in your data, and you know where your point is that you're sampling from, where your supposed robot is. How accurate are the sensors you're having, and how accurate are you able in tracking a robot around in a room that you don't know the dimensions of?
The sensors claim that they measure sub-centimeter ranges and up to 350 centimeters. I haven't verified how well that works, and I suspect that at 350 it's going to be almost useless because there'll be some point way out here someplace. What's that tell you? But because of all of the errors I made when I started the simulation, I am fairly confident that it's going to work with some pretty fuzzy data. It's the data, I'm storing data at a lower interval than we're actually mapping at by 2 orders of magnitude, and then merging those together to make geometric objects in the model. So I think it's gonna work. And I'm not too concerned about, really tight tolerances. Because realistically, if you think about, like, you're gonna place a table next to your chair, do you worry about millimeters or, centimeters close enough? And I think it'll be okay. We're gonna find out. That's.
Yeah, but it's mostly in combination with the location that you're sampling from. How do you track the location of the robot? Because if you make a robot and it's starting to turn 360 degrees around, it just never ever turns 360 degrees. There's always like an error right there as well.
Yes, yeah. I do have a magnetic directional sensor on it. So it's not just the distance sensor. But I tried to get that, and I can see that when I put the device together and I twist it around, I get the numbers changing in the data. But I haven't put it all together to make it all play at once. My goal is to try to do that and try to be able to match back to this sort of truth, be able to say, okay, I think I'm here. And then look around and say, does it match close enough to make it work?
My comment is also more in the robot side than this one. Probably an approach that you could explore. It's more like rather than a data, like understanding the whole mapping and trying to do the mapping and navigation. Probably more like a control approach that is more real time. Probably like you can do very basic detect a red ball thing, like a marker that can be either in the code or like an accessor or something,
right.
And then just like the camera, if it's out of the center, then it corrects, the
Sure. Yeah.
And then you just do some with the sensors, wards to not crash and stuff like that. And then that way it's always following you. I mean, that way, you get what you are looking for, that it's following, despite that, of course, you don't get information of the mapping and all the visualization.
Yeah, one of my goals was actually to be able to start mapping from nothing and see what we get. Because I figure when you turn the thing on, it's got to follow. That's the easy part. But if it's trying to follow and the cat walks in front of it, right? Now it's got to deal with an obstacle because it's there and then it's not there. And so yeah, following I think is the easy part. And so I sort of left that out to last because I thought this was going to be more fun to play with. Yeah. Anybody else?
There's a whole discussion going on here, so maybe it's relevant.
Yeah, it's probably it.
I think this problem is kind of similar to autonomous vehicles, where you have Waymo, who's trying to map the entire city, so that they can use traditional algorithms to navigate through it, like eStar. Then you also have Tesla, that's not trying to create a state of the world, but just uses AI, good vision models, even LLMs to navigate the world. I think that's another approach. You won't have to keep any state. No RDF, nothing, just vision transformers and LLMs to solve this problem.
It's designed to work from no state, right? But
Yeah,
but I thought, I have to do this to figure out where I'm going.
You don't have to.
I mean, well, you got to figure out where the barriers are to navigate around them. Right?
Yeah, for example, if you have a camera and you're, I don't know, feeding 30 FPS to a good computer vision model, it can just see the state of the world without you having a standard graph representation of it. And then if it also somehow has more context about your house, and it could be in several ways, then it would know also, for example, what is behind the door and things like that. And that way it could create a plan of how to travel without needing to represent it in a structured way.
Okay, yeah, I see that.
Just a small comment on that. I think that's exactly the problem with this area. Only 1 year. Right. I think that's exactly the problem we discussed earlier. It's throwing money at a problem to solve it while it could be solved in a very simple way. We have computer vision transformers and everything. That's very computationally expensive. That's very expensive to set up. But this is a relatively simpler problem in a confined space that can be solved in a simpler way, which is what we have presented. So it's about finding that balance of what's optimal rather than just.
Yeah, I don't have the money to pay for that. This is already expensive enough. Yeah. Thank you.
So similar on the same lines. Of the project, and I do want to see it in an end state, but just dumbing it down as much as possible. Why not a string on a card and make your wife put this? No, as in, why not have a just follow me kind of sensor, air tag, as you were saying, rather than having the whole robot figuring out the lay of the land.
What's the fun in that?
Fair enough, yeah.
It's gotta be fun to build, and it's gonna be a challenge, but no, yeah, basically, she could have pull a cart, put it on a cart, and multiply it, that would work. I just can't see her going for that, though. To be honest, that would be like, I'm not doing that. That's one of those things. Yeah.
All right, follow-up discussions in the networking. Thank you, Claude, again, and Derk for your.
Thank you.